and welcome to Dr. G's Technique of the Week, Precalculus Edition.
Today we're going to be looking at exponential functions and applying them to compound interest models. An exponential function is a function of the form f of x equals b to the power x, where b has to be positive. It can't be equal to 1, since 1 to the power x is always 1, so that's a little bit boring. And x, the exponent, has to be a real number. In the case where b is greater than 1, we get exponential growth, which graphed looks like this. We have the x-axis as a horizontal asymptote, and our function gets closer and closer and closer to 0 as x gets more and more negative, but as x grows, our function just shoots up. In the case that b is between 0 and 1, we get exponential decay, where as x becomes very negative, it shoots up, but as x becomes more and more positive, larger and larger, our function approaches the horizontal asymptote at the x-axis, so it gets closer and closer and closer to 0. Exponential functions are really, really useful when it comes to modeling the growth of loans and investments that collect compound interest. So, I want to consider a loan that starts with a principal amount of $5,000, collects interests at a rate of 6.5%, and is left alone to gather interest for 10 years. And there are different ways to compound interest. Sometimes it's compounded annually. It can also be compounded more often. It can also be compounded continuously. So we're going to look at the simplest case first, which is if it's compounded annually, in which case the amount that is owed on this loan at any given time is equal to the principal amount of the loan times 1 plus the rate of interest, in this case 6.5% or 0.065, taken to the power of t, which is the amount of time or the number of years that this loan is sitting and collecting interest for. So take a moment now, using this formula, see if you can find how much money will be owed on this loan after 10 years, given a principal loan amount of $5,000 and an interest rate of 6.5%. So by using this function with a principal of $5,000, an interest rate of 0.065, and a time of 10 years, just putting this into a calculator, we can find the amount owed at the end of that time as being approximately $9,385.69. Now let's see what happens if the interest is compounded more often. Now in this case, two things change about our equation. One is that each time the interest is compounded, rather than being compounded at the full 6.5%, it's compounded by the rate divided by the number of times per year the interest is to be compounded. And our power is changed to the time times the number of times per year that the interest is compounded. So the number of times per year times the number of years. So this exponent will be the total number of times the interest is actually evaluated and added onto the total of this loan. So see what this changes about the total amount owed after 10 years if we were to compound monthly. So n would be 12 times per year. So if we do that, our principal amount still being 5,000 our rate of interest still being 0.065, but now compounded 12 times per year for our 10 years. We find that we now owe a little more money at the end of that 10 years, $9,560.92. So almost $200 more. As this would seem to indicate, the more often interest is compounded, the more interest ends up getting added to the loan or the investment. And you could continue this all the way down to a continuous compounding where at any given moment you are adding interest. And that gives us the principal loan amount times E to the power RT, where R is our interest rate and T still is our time and number of years. So for this continuously compounded interest, using our same amounts, our 10 years 6.5% interest with a principal loan amount of $5,000, see how much we'll owe at the end of 10 years using continuous compounding. If we put in 5,000 for our principal amount, 0.065 for our rate, and 10 for our number of years, we find that we owe, again, a little bit more than we did before with $9,577.70. Now it's time for you to get some practice with these new ideas. See you next time on Dr. G's Technique of the Week.